So hello and welcome to the MoldX 3D webinar series. My name is April Brown. I'm the applications engineer from MoldX 3D North American office in Farmington Hills, Michigan. Today, we're going to be talking about maximizing sustainability through simulation in MoldX 3D Studio. Okay, in today's topics, we're going to talk about why should we be passionate about sustainability and what can CAE do to provide reliable solutions. So we know simulation can allow users to test various design alternatives and what if experiments to identify workable solutions or design problems at the designing phase, molding difficulty. But what about recycled material? So we'll look at what tools are available for recycled material selection, like the software sensitivity to material viscosity, which get impacted by the regrind percentage. For process optimization, we'll show a live demo of MoldX 3D DOE functions, as well as lightweighting options and using our ISLM for energy conservation. So why am I personally passionate about sustainability? Well, over 20 years in manufacturing, I've always strived to reduce waste, cut manufacturing costs. However, I've witnessed and unfortunately been a contributor to waste in material at engineering trials and other costs related and troubleshooting. So that's me in a 2,500-ton press with parts larger and weigh almost as much as I do. So you can imagine the amount of material waste and defects in troubleshooting, as I'm sure many of you can relate. I'm a longtime user of simulation technology, and I know that it offers a powerful avenue to model and test various alternatives and those what if experiments. So it allows us to explore various scenarios and their environmental implications. So let's look at the impact of unnecessary cost incentive and time-consuming holding trials. Best time to evaluate your part is before tooling is kicked off to avoid costly changes, including engineering hours at mold trials. So by effectively utilizing simulation technologies in the molding process, we can significantly reduce the time and costs associated with mold trials. This optimization leads to more parts produced per hour, lower material waste, mold reworking costs, and utilizing machine integration through our machine mode can lead to faster time to market and energy savings. Integrating these tools with the manufacturing process enhances efficiency and profitability. So the simulation software in CAE can offer valuable insights during the design phase, minimizing the need for repeated trials and errors. And these technologies help detect potential molding issues early on. You know, the reworking costs, material waste, again, leveraging these tools effectively can drive progress towards more sustainable and environmentally conscious manufacturing practices. So let's move on to recycled materials. Waste is gaining greater attention and solutions are in demand. So Due to the exhaustion of resources and the requirements for environmental protection, all countries are advocating the concept of sustainable development, especially for plastic products to reduce and reuse. Well, in recent years, various countries have proposed various regulations or policies hoping to achieve a balance between economic development and environmental protection and make full use of plastic products and economic activities with minimal environmental impact. Although many have been implementing the concept of design for recycling and some have already succeeded, it still remains a challenging task. As a designer, you're very likely to face these problems during product design process, such as how do you find suitable recycled materials that have similar properties as virgin plastics? How to reduce uncertainty when working with recycled materials? How to validate the right product designs and ensure product quality? And how to reduce the cost of rework and scrap during manufacturing. So these problems may seem daunting at first, they are, but they will be a lot easier when you have the right tools. Choosing the ideal materials in the design phase is crucial to reduce the failure rate in production, and it guarantees good molding behavior. However, recycled materials have very different physical properties compared to virgin materials, and that's due to the molecular structure, breakdown, and the number of regrind cycles. So to get accurate material data, you can submit a material testing request to MoldX3D's Material Characterization and Research Center. This is equipped with high-quality measurement instruments and ISO accreditation. Our MoldX3D experts will run controlled measurement tests on the provided recycled material and virgin material. Material data will be available via a custom app, which will then include shear viscosity and 5 different mixing percentages and how shear viscosity will be affected by the number of recycling. This will help you find the blends with similar processing properties to the virgin plastic. So let's look at the case in this automotive. Because this bumper is so large, we need to pay attention to the differences in flow behavior, the sprue pressure, and the clamping force. So the initial molding conditions are based on the best conditions of virgin material. It is worth noting that different from the phenomenon that the viscosity of the recycled plastic decreases, the viscosity of the recycled PP selected here is larger than that of the virgin PP. In the process of remelting the recycled plastic, there will be some chemical reactions to increase the molecular weight. Various reasons may cause the viscosity of the recycled PP to increase, but subsequent comparisons will only be made between virgin PP and 100% recycled PP. Because the viscosity of the recycled PP is higher than virgin PP, it has a great influence on the filling behavior, especially on large objects. Compared with the flow behavior of virgin, the recycled has obvious hesitation in the center and on the edges, both sides of the bump. So these images are showing the iso contour of each time step in the filling. So the smaller distance between these curves, they're showing a slowing down or a hesitation in the flow. So with 100% recycled resin, you can see that the sprue pressure reaches the upper limit of the injection machine, plateaus, so the flow rate drops and causes that hesitation. Because the sprue pressure of 100% recycled content is the largest, well, so is the corresponding clamping force. If the clamping force is not enough, it is easy then to cause flush. So to solve the filling problem caused by the high viscosity of the recycled PP, the most convenient method is to adjust the melt temperature. So increasing the melt temperature of the recycled PP can reduce the viscosity of the recycled PP to be the same as the virgin. So in this way, the filling behavior of the recycled material is similar with that of the virgin. So after increasing the melt temperature for the recycled, the melt front of the recycled is now similar with that of the virgin. So the flow front hesitation has now improved. Also, after increasing the melt temperature, the viscosity, the recycled, is now close to that of the virgin. So the sprue pressure of the recycled is similar in that of virgin, so no flow hesitation can be found during the filling. And then, of course, that leads to the clamping force. A lower sprue pressure ultimately leads to a significantly dropped clamping force and now falls into the appropriate range, which happened to be 52% lower. So you might be thinking, well, how many iterations do I have to run to find an optimized condition for my part? I mean, this seems like a lot of work, right? Well, you don't have to spend countless hours setting up multiple iterations. Using design of experiments, Moldex 3D has DOE Wizard. A DOE analysis is easy to set up. It's a step-by-step, and experimental runs are created automatically. So this is an amazing tool to optimize designs and process. So now I want to show you just how easy this is. A lot of you might be familiar with this part. We've showed it a lot in our demonstrations. But you always want to start out with an initial run, which in this case, we did a full analysis. We're going to go to New Run, select DOE Wizard. From here, you just have your basic information. You can name your DOE, And you might want to make sure that you are assigning your base run. In this case, we're going to use a full analysis with the Taguchi method. So your level of changes, your levels is going to be your number of changes. So as we go through these control factors, we can either have a minimum, a middle, and a maximum. We can increase it all the way up to 5. But keep in mind, the more levels or number of changes is going to increase your number of runs, which then increases your computation time. Your control factors, I'm going to set it up as 4 control factors. And you can see we have quite a long list of different variables here. For mesh, what that means is you can run different iterations using the same parameters. Maybe, for example, maybe you want to run 2 different designs. One has maybe a different wall thickness or some additional ribs to help the warpage. Maybe you're changing gate size or gate location. That's when you would use the mesh feature. And then for material, you can try different materials throughout the run. Let's say you want to use different regrind contents. In this case, let's say we want to try to reduce cycle time. So I want to see what kind of effect melt temperature, mold temperature, packing time, and cool time. And we can change those min and max. The default is referencing based on your run number 1 and also the specifications of the material. Now for quality factor, this is what we want to evaluate or say maximize. Again, we have quite a long list of different quality factors. And as most of us want to know, we always want to know the total displacement, right? Maybe in this case, maybe we want to look at part weight. Maybe we're looking at reducing the overall part weight. We can also look at volumetric shrinkage. Now for warpage target value, we're going to put global, which means the overall part. But you can also set up probes. If you're wanting to strictly look at one location, if you're having a problematic area that's creating a warpage concern, you can set this up by probe numbers. We're going to stay with global. And of course, we want the smallest warpage amount. You can also set it up as nominal, where if you have a target value that you want to reach, weight, we also want smaller. And volumetric shrinkage, we want it to be uniform. Now, the weighting of these quality factors can be adjusted. Right now, I have them all equally the same. But by changing this weighting factor, I can say that I want to consider warpage as a higher percent than the other two factors. Hit next. And this now creates our matrix. So this is the number of runs that it's going to assume run by the inputs that you just had given it. And then run 10 is going to be your optimized run. So let's bring in the results. This was a 9 additional runs, a full analysis on approximately a 2 million element count. It took about 4.5 hours for this entire DOE. So if I go down to the DOE results, in the DOE info, you can see your summary page. This gives you all of the outputs of your quality factors as well as your optimized run. If there's any additional factors that you wanted to consider, you can always add those in after you have ran that analysis. One of my personal favorite results is the parallel coordinates plot. So this just graphs out each individual run. And when you hover over each of these runs, it highlights all of your control factors. So now you can see what kind of effect, let's say run number 2, with decreased melt temp, mold temp, packing time, cooling time. It gave us the maximum part weight, the lowest volumetric shrinkage, and we met about in the middle for warpage. So let's just say that you want to meet your minimum part weight. What parameters did those have to consider to meet a minimum part weight? But you're also jeopardizing your overall warpage. So these are just things to consider, early on in your design phases. Maybe we want to consider the lowest possible warpage, but maybe we can meet in the middle for volumetric shrinkage because we haven't built the tool yet, so we can adjust that. Or maybe we can change materials. In the quality response chart, this plot shows us which is more impactful. So in this case, all of your factors had a pretty big impact on your volumetric shrinkage. But if we go to part weight, the only one that had the biggest impact was melt temperature. And then for warpage, we have packing and cooling, which is understandable. Now I wanted to show you one more feature other than our DOE. On your initial run, you can also do a create runs wizard. So in this wizard, you're going to have your base run, and you can have a number of runs based on the same criteria. So say, for example, you only want to change your melt temperature. You can run several different iterations automatically with one click. Now, of course, this method will not give you an optimized. You will have to go into each individual run to see your results. Another nice feature is the run summary. So if you want to compare the results, or I should say your results and your parameters in one quick, easy chart, you can select which one runs you want to compare. You can also change your selected items. And you can export to an Excel file. Okay, the next topic is lightweighting. So lightweighting plays a crucial role in increasing fuel efficiency and reducing CO2 emissions, particularly in industries such as automotive and aerospace. So by incorporating things like film injection molding technology, manufacturers can significantly reduce the weight of plastic components used in vehicles and other applications. So as a result, lighter vehicle parts contribute to better fuel economy. The engines require less energy to propel the vehicle forward. And additionally, the reduction in material usage and weight not only decreases manufacturing costs, but also results in lower CO2 emissions throughout the product life cycle, thus helping us meet the environmental regulations and support global sustainability efforts. So let's look at the example of chemical blowing agents, or CBA. So the great thing about foaming agents is that a standard injection molding process can be used and there's no need to modify the machine. It can easily be added with a mixing blender or hopper. So this chemical reaction forms low molecular weight compounds that act as blowing gas, and it introduces bubbles into the part walls. So let's look at the case of this box geometry. So MoldX 3D can simulate the nucleation and the growth of bubbles when the melt flow is injected into the cavity. It can calculate the bubble size, the number, the density distribution, the volumetric shrinkage. It can predict the interaction between the melt flow and bubble development. It can accurately predict the effects of bubble structure, the part warpage, and weight reduction, as well as evaluate the core-back process. So, of course, the bubble development within the part wall can vary from part to part. However, in the cross sections of this box geometry, the cell size of the actual part compared with the simulation results have very similar trends. So the advantages are manufacturing cost savings and quality improvement. You can reduce the weight by 6 to 12%. reduce cycle times 15 to 35% by using lower melt temps and mold temperatures, smaller tonnages, improve flatness and warpage, high-dimensional stability, reduce stress in parts, and then, of course, a greater design freedom. You can use thinner walls and thicker ribs without any seam concerns. As shown here are both the results of simulation and the real molded part, the warpage direction, and the magnitude of the seam. All right, lastly, I'd like to touch on CO2 and energy savings calculations. So why do we need to support carbon emissions? Well, in support of a global environmental protection, actions are taken to evaluate the environmental impact of human activities, ensuring compliance with EU standards for product production, and striving for goals like tax reduction. In Moldex 3D's ISLN, which is our intelligent simulation lifecycle management, is our data management platform. So users can collect power consumption records for main supply of the injection machine and any auxiliary devices like chillers, hot runners, grinders, etc. So then when the carbon emission calculation data has been filled in, users can obtain the estimated carbon emissions value and power consumption distribution chart and other information in the carbon emissions tab of the project. In addition, the carbon emission calculation report in the solutions page can also be exported to an Excel file. We can take this one step further to communicate and compare your material carbon emissions when using recycled resins and create an action plan for your business and supply chain. Well, this concludes today's webinar. If you would like to learn more on these topics, please consider visiting our YouTube topics on how to know if your simulation picture actually matches reality. And here's more on our DOE module for advanced breakdowns. More information on our ISLM, our data management platform, where you can centralize all of your data, like CAE simulation projects, DFM meeting notes, on-site mold trials, part quality inspection, and simulation reports. Our API, or application programming interface, allows users to create a script to perform commonly performed tasks in a virtual setting. You can run multiple projects using Gate Location Advisor, automatically create cooling, generate mesh, run simulation, and output a report. This is a very powerful tool when quoting numerous tools and the need to utilize your engineering manpower. And we are very excited to announce that next week we're going to be releasing 2024. So there's lots of amazing new features such as solver capability and database, um, new processing and integration tools, project management, and some new modules, including IC packaging. We also have in-person training classes forming at our Farmington Hills office in Michigan. Be sure to look for our upcoming dates. And follow us on LinkedIn and subscribe to our YouTube page where we always have new upcoming information and new videos. So I wanted to thank you again for joining me in this webinar. You're welcome to ask questions, or you can also email us at support@us@moldex3d.com for any additional support.